You flip a switch, and instantly, a light turns on across the room. It feels immediate, almost like magic. But we all know it's electricity. We use it every single second, but how it actually works is one of the most common things people get wrong. So today, let's peel back that illusion and find out what's really happening inside the wire. And that brings us right to the heart of the paradox. Get this, the individual electrons moving through a wire, they move incredibly slowly. We're talking less than a millimeter per second, slower than a snail. So if the little messengers themselves are that slow, how on earth is the message, the light turning on, completely instant? That's what we're going to figure out. All right, to solve this mystery, we have to shrink ourselves down, way down, and take a look at the world inside a normal copper wire. We need to understand what it looks like at the atomic level before we even think about flipping that switch. So a metal wire isn't some hollow tube that electrons flow through. Not at all. It's actually a super dense crystalline structure. The copper atoms are all locked into this perfect repeating grid, which scientists call a lattice. You can almost picture it like a perfectly organized atomic jungle gym. Now here's the really crucial part. For metals like copper, the electrons in the outermost shell of each atom, well, they aren't very attached to their home atom. They're so loosely bound that they can just hop from one atom to the next, creating what physicists beautifully call a sea of electrons. This means the wire's already jam-packed with these free-roaming charges from the get-go. And this sea is not calm. Even in a wire that's just sitting there, not plugged into anything, these electrons are zipping around like crazy. They're bouncing off the atomic lattice at insane speeds because of thermal energy. But, and this is the key, it's complete chaos. For every electron moving one way, there's another moving the opposite way. So the net result? It all cancels out. There's no overall movement, which means there's no current. Okay, so we've got a wire that's packed to the brim with randomly moving electrons. What in the world can organize that chaos and get them all moving in a useful, directed way? Well, this is where we have to make a really important distinction between the speed of the actual stuff, the matter, and the speed of the signal. That push is what we call voltage. The best way to think about it is like water pressure in a hose. A battery or a power plant doesn't create electrons. Remember, the wire is already full of them. What it provides is a potential difference of voltage, which creates an electric field. And that field acts like a giant invisible pump, putting pressure on all the electrons in the wire at the exact same time. And here it is. This is the solution to our puzzle. That electric field, the signal telling the electrons to get moving, it doesn't have to slowly crawl through the wire. It blasts through the entire circuit at almost the speed of light. It puts that force on every single free electron practically instantaneously. So let's just put these two speeds right next to each other, because the difference here is, well, it's just staggering. On one hand, you have the actual physical movement of a single electron, and on the other, you have the speed of the command telling it to move. Here we go. The actual forward progress of an electron, what's called its drift velocity, is less than 1/10 of a millimeter every second. It would literally take hours for one electron to travel a few feet. But the signal, the electric field that gets it moving, that covers the same distance in just nanoseconds. It's an incredible difference. The best way to visualize this is with the classic marbles in a tube analogy. So imagine you have a long tube, and it's already completely filled with marbles, end to end. The moment you push a new marble into one end, a different marble immediately pops out the other end, right? The push traveled through the whole chain instantly, even though each individual marble only moved a tiny bit. In our circuit, the wire is the tube, and the electrons are the marbles. But believe it or not, there's an even deeper and frankly more mind-bending layer to this. If the electrons themselves are barely moving, where is the energy that's actually lighting up the light bulb coming from? The answer is pretty wild. It's not entirely coming from inside the wire. This is such a critical point. The electrons are just the medium. They're the workers on the line. The real work, the actual energy, is done by the electromagnetic field that gets generated around the wire the instant you flip the switch. This field is what carries the energy from the power source to the light bulb at nearly the speed of light. The electrons just react to that field and convert its energy into light and heat. So we know that voltage is the push. But where does that push come from on a massive scale, like the one that powers our entire grid? For that, we need to talk about the amazing relationship between magnetism and electricity. This right here is the principle that basically powers our modern world, electromagnetic induction.
Back in 1831, a scientist named Michael Faraday figured out that you could create an electrical current with nothing more than a magnet and a coil of wire. It was an absolutely revolutionary discovery that led straight to electric generators, motors, transformers, everything.
So here's how it works. Pretty simple, really. You just need motion. You can either move a magnet near a coil of wire, or you can move the wire through a magnetic field. As those invisible magnetic field lines cut across the wire, they exert a force on that sea of electrons we talked about, pushing them along and creating a voltage. That's it. And the really cool part is that we can control this whole process. You want more voltage? No problem. You can either spin the magnet faster, you can use a stronger magnet, or you can just add more loops of wire to the coil. These are the three fundamental levers that engineers pull to design everything from a tiny generator on a bicycle wheel to a massive power plant. Now, that constant motion inside a generator naturally produces a very specific kind of current. And this brings us to the two main ways that electricity can flow. You've got alternating current, or AC, and you have direct current, DC. Just look at the difference in how the electrons move. With DC, say from a battery, the electrons flow steadily in one direction. But with AC, the kind that comes from our wall outlets, the electrons don't really travel far at all. They just oscillate, they jiggle back and forth, about 60 times a second. This just hammers home our main point. You don't need the electrons to travel a long distance to deliver energy. And this quote just sums it all up perfectly. Electricity really is the art of moving energy at the speed of light, while the matter itself moves at the speed of a snail. The energy transfer is happening in a field at light speed, and the electrons are just the medium, just drifting along at a crawl. So let's leave you with a final thought to chew on. We tend to picture our power grid as these giant pipes delivering electrons to our homes. But if the energy is actually flowing in the field around the wires, what does that really mean for our vast energy infrastructure? It's a completely different, and I think much more amazing way to visualize the invisible heartbeat that's powering our entire world.